hear me and do you see? Can you hear me and do you see the screen? Okay.
Yes.
Great.
Yes. Yes and yes.
Okay. Let me just check that everything works. Okay. Okay. Hi everybody. So I can't see. Oh, there. Okay. So I'm David Sanders. I'm one of the co-developers of the JuliaIntervals set of packages. And so we're going to have a session where we sort of summarize the status and future directions of the packages in the JuliaIntervals suite or ecosystem of packages, which are tools for doing interval arithmetic and interval arithmetic-based methods with the Julia language. So this has been a project over many years. We started about 8 years ago, actually, with Luis Benet at UNAM, the National University of Mexico. And since then, many other contributors from around the world have joined and have helped make these packages, bring them to a nice state. In at least interval arithmetic is in a nice state, and everything else is not so far along necessarily. Okay, so I'm going to start with an overview of basically what is the status of interval arithmetic in Julia, and then various other people will talk about other packages. Okay, so first of all, I forgot to say, of course, many thanks to Luca and Marcelo and the other organizers for organizing this workshop and for inviting me to speak. Okay, so we have an implementation of interval arithmetic, and I'll for people who are not totally familiar with interval arithmetic, I'll talk about that in a bit, which is in this package called IntervalArithmetic.jl, and then the JuliaIntervals suite builds on that package. So that's an implementation totally in pure Julia, basically, mainly. And then we have a set of packages, as I said, for interval methods for guaranteed set computation. And so Luca, actually, as part of the Google Summer of Docs, made this very nice web page, which, so this is juliaintervals.github.io, I think, is the address, which basically brings together the documentation, tutorials, etc. on this set of packages. So if you click on packages, you can see the list of the main packages in this suite. And if you click on each of these, you'll have sort of an introduction and tutorial to the main ideas. And if I click on each package, you'll also find lists of the main contributors to the packages. So I'm not going to go through and read out all of those people, but many thanks to all of the contributors who have given of their time to this open source package. I personally think it's critically important that science is based on open source software packages where you can actually go and look at the code, see what exactly is being computed all the way down to the level. All the way down to the sort of bottom level of code. Okay, so why are we doing interval arithmetic at all? I guess that people have already covered that in previous talks. So there are various reasons why we might want to do that. So if we're doing some kind of numerical computation with floating point arithmetic, we want to bound rounding errors in those computations. And it turns out that basically reduces to, okay, I need to have a set that encloses my initial value, and then I want to actually do my computation with the entire set of values. And so basically what it boils down to is wanting to compute the range of a function over an input set. That's the set of f of x for all values x in some input set. And the simplest sets to think of are intervals, so closed intervals like, which I'll denote with the square brackets ab, is the set of all x between a and b in the real numbers. And so we want to use intervals as inputs to a function and apply that function and get out a new interval such that the new interval actually contains the range of the original set. So in Julia, we actually started with Luis working on this as part of a graduate course that we were teaching at the end of 2013 and beginning of 2014, so 8 years ago. And that's when we were trying to learn interval arithmetic methods. And we actually started writing this in Python. And then we discovered, about the same time we discovered Julia, and we just realized that it was so much nicer to write in Julia. So the original reason for using Julia was actually that it was just much nicer to code in. Now, of course, I mean, one of the main interests in Julia is performance. And so later on, so the emphasis first was on getting a correct package, and we were actually using big float for the entire big float floating point numbers with arbitrary precision. These are the MPFR C library. But in the last few years, we transitioned to trying to get a high performance package using normal double precision float 64s. And of course, this is all open source. It has a very liberal MIT license, and it's developed online on GitHub, and everybody can contribute. And indeed, as I said, we've had collaborators from multiple countries, and three or four GSOC students, Google Summer of Code, and one Google Season of Docs contributor, Luca. And this package has got some significant interest from the community. It's been used in several academic publications and other packages. And we are heading towards a stable 1.0 release. So the reason we haven't released 1.0 yet is because in order to do so, we really wanted the package to be compatible with an international standard that I'll talk about later. So actually, in retrospect, I think this was a mistake, and we should have released a stable 1.0 version much earlier. Okay, so again, what is interval arithmetic? I already mentioned. So mathematically, you can talk about this range of a function f. So suppose f is, for example, a continuous function, and we have a bounded set. Then we know that f has, a finite range, and it has some maximum value and some minimum value. And we would actually like to calculate that. That's actually a useful thing to calculate for certain algorithms. Let me just zoom in a bit more if I can. We would actually like to be able to calculate this range, but mathematics gives us no tools to calculate the range. And actually, standard numerical methods also give us no tools to compute the range. It's actually a very difficult problem. It's equivalent to global optimization. We have to find the global maximum and global minimum of f over our input set x in order to compute the range. And we know that this is a very hard problem. It's NP hard, etc. To compute these global extreme values of a function. So that's actually basically impossible. We can do it for simple functions, but in general, it's sort of impossible to do that. So that seems like a problem, but actually interval arithmetic provides a solution in the sense that what it provides is a cheap way to compute an enclosure of the range. So an interval that is guaranteed to contain the range. Okay. So if I forgot to say, if the other people on the call who know about interval, the interval package, if I say something wrong or you want to just add some comment, then please just turn on your microphone. And so I see people writing in the chat, but it's difficult to follow the chat and speak at the same time. So just speak up. And okay, so yeah, so there's many applications, and other people will talk about them. So I'll just skip over this. And some people have already mentioned applications as well in previous talks, very nice talks. So, okay, so how does interval arithmetic work? What we're going to try and do is define what it means to apply a function f to an input interval x. And we want to return something that is the range of f, the upper and lower bounds of f over the input set. And we can actually do this for each elementary function. So for example, for exponential, we would, because it's a monotone function, it's increasing, we would have, if I have an input interval ab, we would have exponential of ab. You just evaluate actually the function at the endpoint, and I get exponential of a to exponential of b. That's a new interval, and it contains exponential of x for any x in this interval because it's monotone. What if a function is not monotone, for example, x squared? Then we'll just take that function and find the pieces where it is monotone. And then we can do the same trick on each of those pieces and then at the end, we'll take the union of the results. And that will also give a guaranteed interval, which is exactly actually equal to the range of the function for elementary functions. But if we have a more complicated function f, that's exponential of sine of something of x, or x plus y, we can have more variables as well. In that case, it turns out that we can only guarantee in general that f of x, that when I put an interval into this complicated function and I pass it through all these intermediate stages, that the output will be an interval which contains the range of f, but it's usually or often an overestimate. So this is called the fundamental theorem of interval arithmetic, the fact that the output contains the true range. So when does this go wrong? By go wrong, I mean, when do we get this overestimate of the range? That's what's called the dependency problem, and it occurs when we have an input that has a repeated variable. So for example, if I have x minus x, I want x minus x to be 0, but if I compute it with interval arithmetic, I get 0, 1 minus 0, 1. The difference of these two intervals is actually minus 1 to 1. So what's happening is that interval arithmetic is unable to distinguish, unable to realize that this x and this x are the same object. But actually the way I wrote it, it's not even clear that they are the same object, and that's kind of the point. But this could be one interval, this could be an x, and this could be a y, and they're completely independent. And so it's true that the correct range is minus 1 to 1 in that case. But if this is actually x minus x with the same symbol x, then there's no way using standard interval arithmetic to actually realize that and compute a smaller containing interval. So, and then this is a big, this is one of the main drawbacks of interval arithmetic, main difficulties. And there are various other, solutions, or not partial solutions or attempts to solve this problem. For example, affine arithmetic, that is another package in the suite of packages, and Taylor models, etc. They are all in a way a solution to the dependency problem. Okay, so as I said, we eventually we rapidly chose Julia. So here's an example of how easy it is in Julia to define a new interval type and then define plus of two intervals, just like this. And then you create those two intervals and calculate the sum. And here is the output of that calculation. It's a new myInterval object with the new low value and high value. And so, it's just a very nice syntax that's very similar to sort of the way you would write something in mathematics. Because I'm using this Pluto notebook, there's a few extra things that I have to write that normally in normal Julia I wouldn't have to write, and it would actually be even cleaner code. So the code is very clean, but it also is actually high performance. So here I'm defining a struct, in other words, a new user-defined custom type. In other languages, in other languages, programming languages, that would be called a class. And so in other languages, when you do this, you actually pay a performance cost from defining this sort of nice abstraction. But in Julia, this has zero cost. This is all compiled away. And so actually, this code is both simple and actually very high performance. I mean, so basically, this will be as fast as if you write this in just pure plain C. And the reason for that is that Julia is doing ahead of time compilation and is compiling this down to machine code. And we could go through and actually look even at the machine code that it's creating. I'm not going to do that now because I don't have enough time, but maybe we can discuss these issues later in the discussion session. Okay, so also I can actually write code that is generic. So with a simple change here, I could just do this and put a T here, and now I have an interval type that actually works for any type that I put inside. So for example, let's just do my interval of big of 1 and 2. And now I have created, big of 1.0 and big of 2.0. Now I have an interval type with big floats inside, and that will, so this is actually it's made so this is a parameterized type, but this code here still works in a kind of generic way. Okay. Anyway, I can write nice and generic code. For example, I can write a multi-dimensional optimization problem just as easy, a optimization algorithm just as easily as a one-dimensional optimization algorithm, actually with exactly the same code. Okay, so more reasons for using Julia is that it's a very interactive language because it's automatically compiling everything, but I can use it in an interactive way, which is so important for scientific computing. The syntax is very mathematical, and we're doing maths effectively, and so we want something where we can easily write. We can use mathematical symbols like intersection. We can use symbols like alpha in our code, and we can also actually use code generation, and that'll be very important in the second part of my talk on on how to use intervals to do constraint programming. Okay, and one of the excellent features of Julia is the ecosystem of packages that have been developed, and I'll show some nice visualizations, for example, using somebody else's visualization package that we can easily use together with our packages. So here's a simple example of how to use the package IntervalArithmetic.jl. So in Julia 1.7 or in this Pluto notebook, you can just do using interval arithmetic, and even if you don't have it installed, it will either it will basically install it for you automatically. This loads in the interval arithmetic package, which is basically just a set of functions objects and functions on those objects. And so let's define a generic Julia function y squared minus 2, and now I'm going to define an interval object using this dot syntax. So 3.4 creates an interval, which is by default with float 64s inside. And by the way, this syntax ... unfortunately, there was a discussion just now, is now used by quite a few different packages in slightly different ways, because it turns out that intervals are useful even if you're not doing interval arithmetic, just as sets. And so now this is used in quite a few places, and so that's starting to be a problem. But anyway, so now if I do f of x, that's actually using the overloaded versions of square and minus that we've defined in the package. And you can see that immediately we get the result that the answer is the interval 7 to 14. So what does that mean? It means that, again, that is the range of this input function f, or perhaps it's an overestimate of the range. In fact, in this particular case, since there's only one usage of the variable in the expression, it's the exact range, but in general, it will be an overestimate. So for example, if I did y squared minus 2 times y instead, I believe that will, so if and then if I changed this input interval to say minus 3 to 4, that would actually now give me an overestimate of the range. Because I'm using y twice, I have this dependency problem that I was mentioning. Okay, so what do we know? We know that, yeah, as I said, f of x lies between 7 and 14 for any x in this input. And I can check, for example, that is 0 inside this output. And here is an example of using, a Unicode symbol, this nice mathematical set membership symbol in Julia as just in code. And that the answer is no. And so what does that mean? It means that 0 is actually not in the range of f. And in other words, we can conclude that there is no root in the interval f. That there is the function f has no root in the input interval x. So that's one of the examples of how computing a range can actually tell you something very useful about a function. If we're looking for roots, which is a very common thing, for example, in scientific computing, interval arithmetic actually helps a lot with these techniques. In fact, it's really the only way that we can guarantee to compute that we have correctly computed roots and found indeed all of the roots. And by the way, we can actually extend these things to semi-infinite intervals. So we have this infinity symbol, which you can just type by \infinity. That's just, so what is that? That's just, that's something we've introduced in the package. And there's some debate about whether that's a good idea, because that, again, conflicts with another package. And so we should combine, with them. So 3 dot dot infinity is a semi-infinite interval from 3 to infinity, and I can apply my f to that interval sometimes and get 7 to infinity. And so I have actually proved that there is no root of f in this entire semi-infinite region. So you can see that it's a pretty powerful technique when it applies. Very powerful technique when it applies. Okay, so that was just a sort of brief introduction to how the package is used and what does it do. Now I'd like to actually talk about the status and of the software tool itself, and what do we need to do to improve it, basically. So how do we know that the code is correct? So we're claiming that, I've just done a computation using floating point arithmetic, and I'm claiming that that proves a mathematical statement that, this function has no root in that interval. And that relies, so mathematically, the mathematics is sort of clear that if you can do this computation with intervals, then that is the correct result. But then you can worry, is our code actually correct? So one answer to that question is that we think it's correct because there are lots of tests. So I'm going to say more about tests in a minute. So we do have thousands of tests that we run every time we modify the code. On GitHub, you can set it up so that it automatically runs a lot of unit tests and will tell you if any of them fail. But there are actually over 100 open issues on the repository with bugs or minor fixes or even some kind of more major issues that a lot of which are sort of design questions. And it's actually, the moral is that it's actually really hard to implement, complicated software in a robust way. So interval arithmetic in principle is actually, the idea is pretty straightforward, and the implementation doesn't seem like it should be that difficult. It could almost be basically a homework for an undergraduate class. But actually getting all of the little details right is really hard because floating point arithmetic is pretty complicated. It has all these edge cases. There's numbers that are very close to zero. Denormal numbers or subnormal numbers are very tricky, etc. So there's all kinds of implementation issues. And then it's also not even necessarily clear exactly what you want the sort of semantics or the meaning of some computations to be. For example, if you have an interval containing 0 and you divide it by another interval containing 0, what should the result be? Should that be an error, or should it be give you minus infinity to infinity? So just sort of understanding exactly what the result even should be is not so obvious. And then there are also other kind of difficult design questions. So this is one of the most difficult that we've had a lot of discussions about. This is one of the difficult problems. So suppose x is the interval from 3 to 5. Is it true that x is bigger than 2? So I think everybody would agree that x is bigger than 2, whatever you mean by bigger. Everything in the interval is bigger than 2, and so it makes sense to say that x is bigger than 2, maybe. But is it true that x is bigger than 4? Well, 4 is in the middle of this interval. So some of the interval is less than 4 and some is bigger than 4. So what should we even answer to this question? So this is the current answer that we give in IntervalArithmetic.jl. 3.5 is bigger than 4. That's the question that I'm asking Julia. This is actual Julia code, and I'm running it, and this is the output, false. So it thinks that 3.5 is not bigger than 4. Which is sort of strictly true because, there are it's not true that all of this interval is bigger than 4, but it's also wrong because some of this interval is bigger than 4. So the correct answer is somehow true and false at the same time. And there are, that's often, if you read interval arithmetic books, they say, oh, this should return a sort of, the set true and false at the same time. And so this really causes trouble with other packages in the Julia ecosystem. If you have a package which thinks that you're feeding it numbers, but you feed it intervals instead, and then it's going to do some computation like this. It's going to check if your input is bigger than 4, and if it is, then it'll do something. Then this will actually give you the wrong answer for part of your input interval. And so there was been a big discussion, mainly led by Joshua Gravita, and he actually basically produced this new package called IntervalsJL, which basically is a wrapper of IntervalArithmetic.jl, except that it redefines these functions, these Boolean functions, such that they only work if the interval that you are feeding in is really a number. In other words, it's something like 3.3 or 3.1 3.3. So it's a thin interval which just contains a single point. In that case, it really is true that it's a number, and you can really say whether it's bigger than 4 or not. But if it's an interval, then it no longer makes sense to he would say to do this, to return true or false in this case. And so he very neatly actually solves the problem by returning missing for these situations. And this missing will go through and poison the rest of the computation. And so basically, if you pass in an interval into these other packages, basically they'll just sort of return missing and they won't do the calculation, or you'll immediately realize that something went wrong. So this is a kind of three-valued logic. Basically, we are forced to have three-valued logic by even posing this question with intervals. So in the interval standard document that I'll talk about later, this is not even defined. So we don't even need to define in the package what it means for something to be greater than something. You rather, instead of that, there are functions such as precedes. Okay, I don't remember the name, but there's a series of functions which define something called Allen's interval algebra, and they basically are words that say, oh, does this interval contain 4, and is this interval completely below 4? Does this interval overlap with 4, etc. Yeah, so intervals of Booleans are available in some tools such as IBEX. Yeah, sure. So we could easily do that, right? I mean, we could just return, basically you could return the interval 0 for false, the interval 1 for true, and the interval 0, 1 for this intermediate result. You could certainly do that. That's a good solution, which will totally also fail in all of these other Julia packages. So that's the point. So one of the reasons that we want to define operations like this at all is because we're actually trying to have this interaction and this composability with other packages in the Julia ecosystem. And so it's really, that is one of the things that makes these design decisions actually so difficult. If it was just, restricted to our little interval world, then basically you can sort of do whatever makes most sense. But because we're trying to interact with these other packages that don't know about intervals, we have to be careful to interact with them in the correct way. So it's great that we can do this interaction. For example, it's easy to do automatic differentiation using the forward diff package, because forward diff just assumes that you have something that behaves like an arithmetic operation, and then it actually just works to immediately put interval arithmetic into that package. But as I was saying, other packages that are going to do tests like this will start to fail if you do the wrong thing. And so, so I think this is so. For a long time, I was sort of arguing, no, that's it. We won't really want to be able to define these operations like this because we want to interact with these other packages. But Joshua was very, Josua, I don't know exactly how to pronounce his name, was very adamant. And I think he's actually right. I've become convinced that he's right. And at least we should allow this to be configured in IntervalArithmetic.jl. So we should actually have just a way to choose, oh, I want comparisons like this to only work for numbers, for number intervals as he calls them, or I want comparisons to work for as we currently have it. So it just should be a configuration that you can easily change. And okay, so another important, so how much longer do I have, by the way, for this part of the talk? When did I start?
I think you started roughly 30 minutes ago. I'm not sure, maybe a little less than 30 minutes ago.
Okay, oh dear. Okay, so
maybe
very quickly.
25 minutes ago, I think.
Okay, thanks. So yeah, so one key part of implementing interval arithmetic. So there's, we wrote from scratch a completely new implementation of interval arithmetic. And since many of the packages have strained or outdated or not really open source licenses, we couldn't actually look at, or GPL, which we wanted to avoid, we couldn't actually look at much code from other packages. We had to sort of reinvent the wheel, which is a big shame. Anyway, so one of the very difficult things, not very difficult, one of the key things to implement is directed rounding. So what do I mean by that? So if we have two intervals, x and y, previously I defined it just by adding the lower endpoints and the upper endpoints, but that's actually not right, because when I add the lower endpoints, because of the way floating point arithmetic works, the result might be something that I cannot represent exactly as a floating point number, and I'll need to actually round it to the nearest floating point number. And that's what it will do by default. But instead of rounding to the nearest floating point number, I want to round the lower endpoint down and the upper endpoint up. And that's the only way that I can guarantee to correctly include all the possible results. So there are various ways to do this. There's setRounding.jl, which actually changes the hardware rounding mode. This is the standard way to do interval arithmetic that people have been sort of doing for a long time, but unfortunately it's slow, and also it has some technical issues with LLVM when you do it from Julia. So instead of that, there's this beautiful rounding emulator.jl package, which uses a technique invented by Professor Kashiwagi from Japan. I hope that name is right. I forgot to write it down. He has a package called KV for C++ for interval arithmetic, which uses these techniques. So basically, it's using error-free arithmetic, which I'm not going to go into, but it's a very neat trick. And Jeffrey, I'm blanking on his name, Jeffrey Sarnoff had previously written a similar package called fast rounding in Julia. So basically what is the idea? The idea is that when you do the sum of two floating point numbers, it gives you a floating point number as a result, but as I just said, that might not be the exact result. And so this error-free arithmetic actually allows you to obtain the error that you made in doing this calculation exactly using pure floating point arithmetic. Anyway, so we can do rounding of the basic arithmetic operations using either of these methods. For elementary functions like sine, that's actually a really hard problem to do correct rounding. Correct rounding means finding the closest. It should be called closest rounding, really, or it means finding the closest floating point down or up. And there's this package crlibm, and now there's in development various other versions or newer versions of this package, but it's not clear to me that they're ready yet. Anyway, so this crlibm.jl package wraps the crlibm library for correctly rounded elementary functions. But actually, there's an easier solution, which for some reason people don't often talk about, which is just to use previous float and next float operations, which are provided by Julia, and they're very fast, and that's very simple to do. So these just take, given a floating point number, they just move and give you the previous one or the next one in the set of floating point numbers. So the reason I presume that people don't like to do this is because it makes an interval that's slightly too wide at each step. Instead of being one ULP, unit in the last place, ULP, instead of being one ULP wide, it gives you something that's two ULPs wide. And so if you do, a series of computations, then you'll get something that's kind of a bit wider at each time. And if you have a chaotic system, then that's a bad idea, etc. But really, for many applications, I really think that's the simplest and fastest solution. And so, of course, again, the simple thing that we want to do is actually have a way to configure this in the package. And so we did have originally an interval. We had like in the currently released version of the package, we have a function called setRounding, which is not a very good choice of name. So setRounding of interval, comma something, will actually choose one of these types of rounding mode for different parts of the system. But it's not is not very well done, to be honest. And so I have a pull request. This is one of the things that going forward, I think is very important to change. We should have a general configuration mechanism for all of these different options that people have been arguing about, right? So somebody wants this thing to behave like this. Somebody else wants fast intervals. Somebody else wants narrow intervals. That's all great. It should just be really easy to configure this in the package. And so I made this pull request a while ago, and it needs tests, and it needs, the usual sort of, it just needs everything to be pulled together, and I haven't been able to do it. So if somebody would like to help, that would be great. It just has this configure bang function, and you sort of just specify, the different configurations. So for example, I want fast directed rounding using previous float, and I want fast powers. So powers of intervals turns out to be a big pain as well. And if you want exactly correctly rounded powers, you have to actually use MPFR, which is terribly slow. And so instead of that, you can have something that's slightly wider and much, much faster. But again, that's a choice that you want to be able to make. Do I want, as tight as possible, or do I want as fast as possible? Anyway, so this is just a general mechanism for configuration that should be, easy to add other things to, for example, this number interval business, etc. But just to point out that this actually is redefining a lot of functions in the package when you call this, so that they behave in a different way. It's not ideal to do that at all, but that's the simplest solution that I could find, and Julia allows you to do that. So if you redefine a function in Julia, it will automatically redefine all of the functions that use that function inside. And so, and it doesn't even take that long to do, but it is recompiling all those functions. So you only want to use this really once in a program, or, a couple of times in a program. This is not something that you want to be doing all the time at all. But there's no reason why you would want to do it all the time either. You just set these things once at the start of your program and leave them. And of course, you might want to run it several times with different configurations to check which one is faster or slower. Okay. So there are various different things that should be configurable. I've already mentioned them. So I should say something about, before finishing, about the standard. So there is this IEEE standard 17882015 for interval arithmetic packages. It defines, some sort of minimal basic requirements for what an interval arithmetic package should look like. And we've been trying to work towards compliance with this package, and it's actually quite tricky to do that. One of the reasons is it doesn't say how to implement the required operations, and it's often hard to read and even ambiguous. Or at least it sort of doesn't specify a lot of the things that we have questions about. And so, yeah. And so I'm going to skip over decorated intervals because I don't have time, but it's an interesting subject. And so how do we know whether we're compliant with the standard? Nobody actually, you have to sort of decide that yourself almost. And to do that, there's a sort of this semi-official test suite called ITF 1788. And it's very interesting. It specifies a lot of tests in this sort of special specification language called ITL. And then Luca wrote this ITF 1788.jl package that actually runs all those tests from Julia and generates Julia versions of the tests. And so that's what we're running against. And we also have some tests that we wrote. And that's what we're running against. And so, that proves that this package is, quote, correct. But of course, it doesn't prove it because there's still a lot of corner cases, etc., that are not covered by the package or whatever. Okay. Okay, so there is this big issue that Luca wrote that summarizes all of the current issues that we have, which are not compliant with the standard. There are some bugs. There's exception handling missing. There are reverse functions that we need to finish implementing, etc. And of course, help is always welcome. Yeah. Okay, I just wanted to mention the ARB package. There's a Julia wrapper of the excellent ARB library by Frederick Johansson, which is a ball arithmetic library, so basically does midpoint radius arithmetic. And it would be nice to have a midpoint radius implementation in Julia with pure interval float 64s. I haven't done that. Yeah, I'm not sure how difficult that would be. I don't think it would be too difficult. But arb has arbitrary precision, and it has a lot of special functions implemented. And so we should definitely be wrapping those special functions, from interval arithmetic. Special functions, I mean like Bessel and error function, etc. So in future directions, the package has been stable for a long time. That's why I said we should be releasing 1.0, except for this configuration business, which is important. And it can even be used on GPUs. I've shown this in a few recent talks, because that's nothing to do with interval arithmetic. That's just the amazing nature of CUDA.jl, which just takes the code and compiles it to the GPU. Float 32 and float 16 intervals is a weakness that needs quite some work. It should be easy to do that, but it just requires going through all the constructors and functions and things and just making sure they work properly for float 32 at least. Float 16 support in Julia is actually not that great, but wait. So there are some performance tweaks probably that could increase the speed of some functions, although we have optimized most of the functions, like main functions, quite a lot. But I have been playing around with different ideas. For example, if you redefine how we represent the empty interval using nans instead, then that might be more efficient, etc. And it would be great to be able to work with intervals that contain intermediate precision types. So there's great multifloats.jl package, for example. But the way it does the computations is actually not clear. For example, I think it's not even clear how you do previous float and next float, which is key for interval arithmetic. So that needs some thought to be able to use those. And so here's a more crazy idea. So dependency analysis is this thing I was talking about of if you have a function x squared minus 2x with the x appearing twice, how do I even recognize that x appears twice? Standard interval arithmetic cannot do it. So one idea is to use symbolic manipulation. So there's this great symbolics package, and I'll talk about it more in a bit, where I define variables and then I pass in a symbolic variable into my generic Julia function, and it gives me a symbolic representation of that function, if the function is like just a normal mathematical sort of expression. And now I have this symbolic version. I can actually check that this z and this z are actually the same object. And so now I have a way to actually analyze dependencies in my Julia expression. And so that opens a lot of doors, and it's just a question of working out how to exactly exploit that. So now I know that, oh, this is a function of one variable. That's the same variable. Now I can do a lot more things that I couldn't do before with normal interval arithmetic.